Cauchy's first theorem on limit. What does it say? Theorem wise, it is very simple. It simply states that if there is a sequence which is converging, sequence is converging, meaning a n limit n tends to infinity is equal to L, then the mean of sequence, that is summation of the terms of the sequence up to n divided by n, if we take limit n tends to infinity, this will also converge to L. Here people get confused is not the theorem, what it is saying. The point that I will be discussing here is about the proof. If you understand the proof once, the concept becomes very much clearer and you might never forget this theorem. Anyway, this is so simple that you in either way also you do not forget it, but it is very good to understand the proof of the theorem. Proof is, to some people it seems slightly tricky, so let's understand the proof. What we are going to do here is that since in the denominator we have a term n, as in we are averaging out n number of terms of the sequence. Normally what we would do is that to prove this, we will take the term here is for this sequence, that is average. How will this sequence look like? Just look at this before we delve into the proof of this theorem. Just so the first term will look like this. Let me represent the terms by saying T1. T1 will be something like this, T2 will be something like this, T3 will be something like this. Similarly, Tn will be something like this. Right. If we keep on going till infinity, the final term, as in the converging term, will be L. The final term will converge towards L. Better not say final term, we can say that the term at a very large distance will converge to L. So we are saying that this 3 is there, 2 is there, and n is there. Likewise, if you want to prove that this sequence is converging, then what we will have to prove is that this, normally this is what we will have to prove, that this should be this for a given epsilon, greater than 0, epsilon greater than 0, this will be very small epsilon greater than 0, this the Tn minus L will be less than epsilon for n greater than equal to m. This simply means that we have T1, T2, n equal to 1, n equal to 2, go on, so on, n is equal to m. We have Tm and then with Tn. As soon as we go beyond this mth term, the difference between the terms after mth term and the mth term, that is Tn minus Tm, Tm minus Tm, sorry, just give me a second. So as soon as we go beyond this mth term, there is a number L from where the distance of any of the terms from this L number, the distance of any of the term from this L is less than epsilon if we go beyond the mth term. This simply means that the sequence is converging to L. This is what we would have proven normally, right? That this should be true for any n greater than or equal to m. We would have looked for this m as a function of epsilon, because this will depend on epsilon. Because let's say epsilon is equal to 0.00002. For this, I want that the distance is less than epsilon equal to 0.00002. For this m, there will be corresponding m, that is m1, right? If I want this epsilon to be less than 0.0000002, then for this m1, this m will change, right? M2. So this m is clearly a function of epsilon. The moment you change this infinitesimal number, the value of it, m changes. For any n greater than this m, the distance from L of the term, Tn term, where n is greater than or equal to m, will be less than epsilon, right? So normally this is what we would have looked to find out the m for this less than epsilon. So proving this is possible, but a little challenging. So for the simplification purpose, I might think of talking about why it is a little challenging, but you will in some other video. But on the way also, as I proceed to prove this theorem, you might also figure out why it might have been a little cumbersome. So better to make the process simpler. I will do that. Otherwise also it can be directly proven as well, but let's focus first on the conventional proof, the proof which is there in most of the books. What I am going to do is that, so just focus here. We are given with this, and limit n tends to infinity is equal to L. We can, if we can adjust this. Can we say this? This can also be said, right? That n minus L limit n tends to infinity is equal to 0 because n is ultimately converging towards L, right? If I take this as Bn is equal to n minus L. Why I'm trying to take this as Bn is that if I do this, I might be able to get rid of this extra L here inside this, and this will make our life easier in terms of proving and finding M. We are always looking for that M, n greater than equal to M. We are always looking for this M as a function of epsilon whenever we are going for this kind of proof. We are always looking for this M as a function of epsilon. So finding this M will become easier at the moment we are done with this extra L minus L, because subtraction, division, less than epsilon, something here, something division divided by this less than epsilon, we are easily able to just swap this and just n greater than some delta function of epsilon we are able to find, right? Just look at this. Bn is less than, Bn is equal to, we are substituting an with, Bl plus L. Here where Bn limit n tends to infinity is equal to 0. We know that if a sequence is a converging sequence, if you are able to recall from whatever you would have studied, that if a sequence is a converging sequence, it means, let's say, it means this, right? So any of the term of the sequence can be will be from this set, not can be, any of the term of the sequence will be from this set for epsilon n greater than equal to some M. This M plus 1, M plus 2, dot dot dot, L plus epsilon, right? So when the sequence is converging, it means sequence is bonded as well, where M is max of this set S1, right? This is also bonded. It means that Bn will be bonded. We can say that Bn is less than M. Now focus on this. What I am saying is that mod of Bn will be less than M for every n less than equal to M, and mod of Bn will be less than epsilon for every n greater than equal to, better say, M1. I'm taking epsilon as epsilon by 2. There's no harm, right? Because this will be, it will be better for us to show that this is less than epsilon, the final version is less than epsilon. So for that purpose I am taking it epsilon by 2. Now, so if I simplify this, mod of A1 plus A2, this is finally what we intend to prove, right? But that this should be less than some epsilon for a particular some n, certain M. If you simplify this, if we are simplifying this what we are getting is that b1 plus b2 plus dot 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 plus bn by plus nl divided by n minus l. See, we are done with this L term, right? Now this we are left with some simpler expression. Just focus here. What we are saying is that for certain n less than equal to m1, we are saying this bn is less than m, the mod. Can we write this? We are just splitting it up till the term m, plus we know this, right, property mod of z1 plus z2 is an equal to mod of z1 plus mod of z2. We can write it simply like this, right? Why we are splitting is that just which I'm just trying to I'm in next few minutes or so I'll be explaining to you something which generally are not shown in the books. Just focus here for a moment. I'm just stopping this. I'm not proceeding with this proof. I'm trying to explain something which is generally skipped in the book, and students struggle with that thing normally. Why I have stopped here, right? Why did I say that let's take this mod of bn is less than epsilon? I'm splitting this in first m term and then after that next m plus n terms. If I see these terms on the number line, for a sequence which is increasing, the sequence might be increasing, decreasing, or whatever, increasing then decreasing, we don't care about that. This is not a number line, please pardon me if it might seem like. So first let me write this b1 bm, then bm plus 1 up until bn, right? We are pretty much sure that when n is greater than m1, this should be m1 plus 1, something like that. We are pretty sure that when this n is greater than m1, this bn, the mod of that is less than epsilon 2, right? These terms, we are okay with these terms because this is converging towards L, right? Not towards L, in this case 0, right? Because we have replaced an with bn. But we do not know about these terms. We cannot directly say, that b1 is mod of b1 is less than epsilon by 2, because here n is less than m1, and for this we can't say this, but we can say this, that mod of b1 is less than the m, the supremum, right? This will always be true, no matter whether n is greater than m1 or n is less than m1, right? it is also freeing us. It is also freeing us from looking at looking at the increasing decreasing nature of the sequence. It has also freed us from that, right? So this is what I was trying to explain before we proceed. Now let's proceed. I'll just rub it. So what we can say here is that all the terms are less than equal to m. So m into capital M into small m1 divided by n plus epsilon by 2 minus m1 divided by n. This is what we can say. This can be written as n m1 divided by n plus, look at this term, this is nothing but less than 1, right? So epsilon by 2. Focus on this term. M1 is fixed, small m1 is fixed. It will vary, but for this term sort of fixed. Small m is fixed, sorry, capital M is fixed. We are left with this. This will converge, right? This will converge. So m1 by n. This will be a certain m1 dash, m1 triple dash. Based on what epsilon you will be choosing, this might change, but this will be a finite number. N here will keep on changing. N here will be taking you to infinity or whatever. So if I say that this is less than epsilon by 2 for every n greater than equal to m2, right? Can we say that? Yes, we can certainly say this. There's no issue in that. Now we can write that this is less than epsilon by 2 plus epsilon by 2, nothing but epsilon, for every n greater than equal to max of m1 comma m2, right? So we are done with the proof, right? This is where, so I wanted you to focus on couple of things. First is the replacement, why we are replacing it with n minus l. Second is with respect to this m1, why we have chosen to split the whole expression into these two subparts, and then focusing on this and this. That's all. If you are focused on these 3-4 things, you will always remember the proof, and also you will understand how the proof is working, how the process is working, right? So that's all. Thank you. This is all about Cauchy's first theorem on limit. The theorem is very simple. The thing that you need to understand is the proof. Thank you.